Today I'm just going to review some periodic trends. Some of this we've covered in previous classes, and some of it's going to be a little bit new. But I just want to go over the logic behind the periodic trends, and then a brief review of what they are, and some exceptions to the trends that we'll see in this class that we haven't talked about before. So this corresponds with sections 8.4 through 8.8 in your notes, and you can also find it in your textbook. So hopefully everybody should remember the difference between valence electrons and core electrons from your previous chemistry classes. But just as a review, valence electrons are those that are in the outer energy level, and they're the ones that are important for chemical bonding. The core electrons are the ones that are in the complete principal energy levels. So any level that doesn't have any more room, that would be considered, those would be considered core electrons. So just as an example, here we have the electron configuration for silicon, and you can see that the 1 and the 2 energy level are completely full. So those comprise our core electrons, and then in the third energy level we only have 2 electrons in the 3p, so all of the 3s and the 3p electrons would be considered valence electrons. Okay, as we move down further and our order for filling changes, so let's take a look at germanium. So here we have 1 and 2 are completely full. 3 is full because you can see we have 10 in the 3D. But the 4th level is not. So here, even though we haven't, it's slightly out of order, just the 4s and the 4p electrons are considered valence electrons. So in this case, we have 4 valence electrons for this atom, and the other 28 are considered core electrons because they're in those shells that are completely full. Now, most of the elements that we're going to work with follow all of the rules that we learned previously in chemistry and the ones you reviewed previously in this class. But I do want to mention an exception that happens because elements tend to be more stable if their orbitals, are either half filled or fully filled. And so sometimes, because that gives just a little bit of added stability, sometimes you get electron configurations that don't follow the rules exactly. And while you don't need to memorize which ones have exceptions, it is important that if you see an exception and you're told it's a ground state configuration, that you can explain why it deviates from the rules that we learned. So the first one we want to do here is chromium. And chromium is atomic number 24, all right? And it is, if you would look at the periodic table, it is 4 spaces over in the 3D. So you would expect that its electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4. Okay, but it turns out that the electron configuration for this one actually ends with 4s1 and 3d5. And this is because having both the 4s and the 3d half full is more stable than having them with one full and the other one with just 4. So it's kind of a weird exception, but that's just spectroscopically when they do the experiment, that's where they find they are. And it's partly because the 4s and the 3d are really similar in energy, and so it's not that much different to be in one orbital or one sublevel versus the other. Okay, and then similarly for copper, the electron configuration for this one, if we do the shorthand, would just be argon and then 4s2, 3d9. Okay, and so the same thing here. The 3d is almost full, but not quite. But if we take 1 electron from the 4s, that would become 4s1, and then we'd have 3d10, which is completely full. And so that just results in more energetic stability. So it's tempting to say as an explanation that the atom prefers to have a fully filled subshell or a half filled, but really it's about added stability. It's a state that has less energy, and that's the reason. So the atom is not a thing, it doesn't think or have a preference, even though we sometimes talk about them like that. So make sure that when you give an explanation for why it's not the one that you would predict based on our filling rules, that it's because it's added stability or reduced potential energy. So now the reason we spent all of this time figuring out electron configurations and determining where electrons are in these different sublevels is because it gives us a tremendous amount of power to explain how atoms behave. So the first thing I'm going to talk about is the formation of ions, and forming ions, cations in particular, involves removing electrons, and so that always requires energy because you're pulling a negative charge away from that positively charged nucleus. And so since it requires energy, you must need to gain some amount of stability in order to make it worthwhile to do that. So it turns out that atoms that are closest to a noble gas configuration are going to be the most reactive and are going to be the most likely to form ions. So let's take a couple of these examples here and explain how we get these common oxidation states. So I had you learn that things in the first column form +1, things in the second column +2, and so on. And then the column right before the noble gases, those are -1, and the ones before that are -2, and so on. So now let's take a look at the electron configurations and refresh ourselves on why they do this. So sodium, the electron configuration for sodium would be 1s2, 2s2, 2p6, 3s1. Okay, so this would have a completely full first and second energy level if it could just get rid of that one electron. And so that's going to add a lot of stability to the atom, or what is now an ion. And so that's why that happens so readily. Okay, so getting rid of this one electron gives you that fully filled core or noble gas configuration, which is just more stable. All right, for chlorine, we have 1s2, 2s2, 2p6, 3s2, 3p5. Sorry, I can't count. And so in order to get to a full 3p, or a noble gas configuration, the argon configuration, we would need to gain one electron. One extra negative charge would give us a -1. So that's why all of the halogens tend to form a -1 charge. All right, the electron configuration for aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. All right, and so we could just get rid of this 1 and the 3p, but really having electrons in the 3s, it doesn't really benefit us that much to just get rid of the 1 and the 3p. So aluminum readily gives up all 3 of those electrons in order to get to that noble gas configuration, right? And then zinc, this one's a little bit trickier. So the noble gas configuration for zinc, the electron configuration for zinc is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then, 3d10. Right? So we've got the whole third energy level completely full, and the first and second are completely full as well. So we just have 2 electrons in the 4s, right? And those 2 are going to be the ones that get removed in order to give us the zinc 2+ ion. So one thing to note here is that we know from experiments that even though 4s often gets filled before 3d, when we're removing electrons, removing those 2 from the 4s is usually easier or requires less energy than removing ones from the 3d if it's completely full. All right, so removing electrons follows a different order than putting them in when you're filling the shells. All right, now we're going to continue talking about periodic trends. And so one of the ones we discussed previously was atomic radius. And so I just want to specify the 2 different ways that you can measure atomic radius. The first is a non-bonding atomic radius, or a van der Waals radius. And you can do this with atoms that can be frozen into their solid form but not bonded to anything. And so once you get them in the solid form, you can measure the distance between 2 nuclei, and half of that distance would be the radius of that atom. So it's not bonded to anything else, it's just packed into the solid form. And so that gives you an idea of what the radius of the individual atom is. The second way to do it is the bonding atomic radius, or sometimes called the covalent radius. And for nonmetals, that's half the distance between two of the atoms bonded together. So, for example, if we had fluorine gas, which is F2, you could look at the distance between those, and half of that distance would be the radius for one fluorine. And for metals, they would be in a metallic crystal, and you would look at half the distance between two atoms that way, so they'd be involved in a metallic bond. All right. Effective nuclear charge is a topic I wanted to touch on because we use it to explain all of the periodic trends. And so effective nuclear charge is basically the amount of charge from the nucleus that the electron feels. And so if you remember, we have discussed this previously. So the effective nuclear charge is called Z effective. Z is the actual nuclear charge, and S, so Z effective equals Z minus S, and S is the charge screened by other electrons. So there are going to be other electrons that are core electrons that are shielding that positive charge from electrons on the outside. Okay, so the more core electrons there are, the more shielding there is going to be that prevents those outer electrons from feeling that pull from the positive nucleus. So we're going to review this in class, but you should remember, hopefully, that as you move down a column in the periodic table, the principal energy level increases, and therefore the distance that the electrons get from the nucleus increases. And so the orbitals get larger, and therefore the radius gets larger. So as we move down a column or down a group, the atomic radius gets bigger. And as we move across the periodic table, we are adding electrons to we're adding protons to the nucleus, and therefore increasing the nuclear charge, but we aren't changing the number of core electrons, because as you move across, we're still in the same energy level, okay? So that energy level is getting more full, but it's not being shielded by any additional electrons, which means that the extra positive charge in the nucleus can pull those electrons in more, okay? So as we go across from left to right, the atomic radius tends to get smaller, right? So we're going to review this, but these are trends that you should know, hopefully, but this can serve as a little bit of a refresher. Now I'm going to talk about magnetism, which is something we haven't really discussed in previous classes. So the first definition I need you to know is paramagnetic, and something that is paramagnetic is an atom or ion that contains unpaired electrons and is therefore attracted to an external magnetic field. Okay, so this is what you would call magnetic. All right, whereas diamagnetic is slightly repelled actually by a magnetic field because all of the electrons are already paired up. Okay, so let's write two electron configurations and determine if they are paramagnetic or diamagnetic. So iron, the electron configuration for iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. Okay, so 3d6. All right, so if we were to write out the electron configuration for that, the only place we could have unpaired electrons is in the 3d sublevel, because all the other ones are full. So if we have 6, that means we have 5 in individual orbitals and then 1 that's paired up. So that still gives us 4 unpaired electrons. So this iron is paramagnetic, and therefore it would be attracted to a magnetic field. Zinc, on the other hand, we just did this electron configuration a minute ago, so I'll just do the shortened version. So it's the argon and then 4s2, 3d10, okay? And since there are 10 electrons in that 3d sublevel, they're all paired up, and so zinc is not attracted to a magnetic field, so it's diamagnetic. The next trend we're going to do is ionic radius. So an ionic radius is just the distance from the nucleus to the outside edge of an ion rather than an atom. So same general idea, but now it has a different number of electrons than the original atom. So cations, we're always removing an electron. So cations are always smaller than their corresponding atoms, usually because we lose an entire sublevel relative to the atom we started with. Anions, however, we gain an extra electron, but we don't put any more protons in the nucleus, so they are always larger than their corresponding atoms. Right? And then the ionization energy is the amount of energy required to remove the first electron from the atom. So it's whichever one would be easiest to remove, so whichever one is in the outer energy level. Okay, and the exceptions that you need to know for ionization energy in terms of trends. So as we go across, let's talk about the trend first. So as we go across the periodic table, like I said before, we're adding electrons to that same sublevel, but we're increasing the number of protons. So it gets harder to pull off an electron because the shielding doesn't change, but the effective nuclear charge is going to keep going up because the charge in the nucleus is going up. Okay, and as we go down, we're adding energy levels, and so getting further from the nucleus, and so the ionization energy is going to go down as you go down a column because it's going to get easier. Exceptions to this are when we have half-filled or fully filled sublevels, and the reason is because of that extra stability that I mentioned in the previous slides. And so if you have, for example, if you're comparing the ionization energy for oxygen versus nitrogen, you would think oxygen should be harder because it's further to the right, and therefore there's a higher effective nuclear charge. But it turns out that because nitrogen has that extra little bit of stability because its P sublevels are half full, it actually is a little bit harder to remove that electron from nitrogen than it was from oxygen. Just a teeny bit, but if you look at a graph of it, you'll see like a little blip in the trend. And again, for these, I'm not expecting that you remember specific exceptions, but if you see an exception or something that doesn't fit with the trend that you're familiar with, you should be able to reason your way through it based on the stability of half-filled or fully filled orbitals. All right, now we're going to talk about just two more trends. The first is electron affinity. So first, let's define electron affinity. So that is the energy change associated with gaining an electron by an atom. All right, and it's usually negative because usually adding an electron releases energy. However, if in some cases it's not. So for example, in the noble gases, there's a lot of energy associated with having to put electrons in a whole new energy level, so it's not negative in that case. But for example, the halogens, which easily take on a -1 charge, those have a high they release a good bit of energy when they gain an electron. So the trend in electron affinity is not super regular, but what you can generally see is that things that are more electronegative, like fluorine, tend to release more energy when they gain an electron versus things that are not don't have that same effect. So generally, as we go down a group, it either becomes less negative or more positive in the case of metals that don't want to accept electrons, or as you go across the periodic table from left to right, as you get more toward the right side, you get more negative electron affinities. All right, and then the last one is metallic character. So metallic character tells you how good at being a metal something is. So characteristics of metals tend to be malleability, so they can be pounded into sheets. Ductility, they can be drawn into wires. They're usually shiny, and they tend to lose electrons in chemical reactions. So metals tend to form positive ions. All right, so this is sort of a qualitative quality or characteristic rather than a quantitative one. So there's not a number associated with the metallic character. So as we go across the periodic table from the metals to the nonmetals, as you would guess, the metallic character goes down. Okay, and then as we go down the periodic table or down the group, the metallic character increases. So as we move down a group, the electrons in the outer shell are held less tightly because they're further from the nucleus, and therefore that loosely held um, electrons is what makes metals metals. And so as we move down a group, the metallic character increases. Right, so it's going to increase as you go down a group and decrease as you go across the periodic table from left to right.